Hello, everyone. Welcome to Call a Doctor. Today, I'd like to talk about what's up and coming for H5pyd. So, H5pyd, if you don't know, it's the client library to HSDS, the REST-based service for HDF. And one of the aspects of H5pyd that's been important is compatibility with H5py. And kind of map that on to the REST API has some challenges. And to address those, there's going to be a very large release upcoming. And so we'll go to from version 0.9 to 1.0 for this. Anyway, so some of the features are improved performance, and I'll explain how that's going to work. There'll be a refactoring to have code that's common to both H5pyd and HSDS to be in one package, and support for additional storage formats. So h5pyd will not just be a package to use HSDS, it can potentially be used for other storage formats as well. So with the good, some things go out. There'll be some APIs that we added recently that they'll no longer be supported. And the rationale for that is that those APIs are not compatible with H5py, and the motivation for those APIs will no longer be needed. So these APIs were added to achieve similar performance benefits that we'll get with this version 1, but at the same time, you won't need to use new APIs. You use the regular H5py APIs. So how the package layout will work is we have h5pyd, and there'll be a new dependent package, h5json. h5json was a package that the HDF Group developed many years ago. I think Jolie here was instrumental in some of that. And unfortunately, we hadn't really capitalized on that. But what h5json does, it provides a way to map HDF5 metadata into JSON objects. And that's useful for HSDS because to communicate to HSDS, use REST API, and in large part, that means packaging in the HDF semantics into JSON formats that can be sent over the web. And at the same time, HSDS uses H5JSON or parts of it as the storage schema. So rather than have bits of code that are disjoint but doing the same thing, now those bits of code will be in common in the H5JSON package. So on the H5pyd side, other than H5JSON, there's some standard packages we use, like h5py to read from HDF5 files. We use the requests package to send HTTP requests. And on the HSDS side, we have h5py, which is used, again, to read HDF5 data. We use the AIO HTTP, which is an asynchronous HTTP package. And we use AIO Botocore, which is an async package for talking to S3. So moving on. And by the way, anyone has a question, feel free to interrupt anytime. So part of H5JSON is this new class that we developed for this release called HDF5DB. And what it is a key value store for HDF objects. So each object, a dataset, a group, a data type, has an object ID, and that's the key in the DB class. And this is used to have like an in-memory scratchpad for common data. So where before we might have said, oh, I need to read this attribute, talk to HSDS. Now, potentially, we can just find that in this in-memory database. And similarly for writing, rather than updates, like create a new group or create an attribute, going directly to HSDS, they'll instead go to this HD5DB. So the current state from the client point of view will not always be directly synchronized with HSDS view of the current state. Instead, it works kind of like you would imagine a journaling file system, right? You do writes, you do writes. The file controller wouldn't automatically move those writes to disk. They would wait to optimize that by packaging a bunch of updates together. Okay, so imagine like in your program, you have a loop and say for, I in the range 1000, create attribute, create attribute, create attribute. Before, that would be 1,000 HTTP requests to HSDS. And that'd be rather slow compared to using h5py and the HF5 library. In the new schema, those create attributes would flow from the client to h5pyd. h5pyd would call a function in this HF5 database, and that would store those attributes in memory. After a certain amount of time, or when the client explicitly calls a flush action, all those updates get packaged together to go to HSDS. So what may be 1,000 HTTP requests becomes one HTTP request. And that really helps because what's taking up most of the time commonly is not work on the client side or even work that HSDS is doing, it's the wait time. You send a request to a server, you're waiting for the response, and there's latency across the wire and such so on. So we eliminate the bulk of that. Another interesting aspect is that the H5DB itself doesn't know how to read from storage or write to storage or read from HSDS or send calls to HSDS. It's a pure key value memory store. To actually read or write, you utilize these plugins. Okay, so you could have, for example, an HSDS reader plugin, uh, and then a HSDS writer plugin. So this enables data to be read from the server, flow into the database, and conversely, updates to the database can flow back to HSDS. And you could even mix and match these, right? You could have, for example, an h5py reader and an HSDS writer. So this would enable you to read from HFI file and copy the contents to an HSDS domain. So I think there's a lot of flexibility to this. So initially, we'll have reader writers for JSON, HDF5, and HSDS. Uh, Eventually, there could be readers or maybe writers for other formats like ZAR or Parquet. And also be interesting to have a reader writer that talks to the HSDS storage schema, but not through the server, but directly writing to storage. So that would enable you to have the functionality of HSDS for the most part without having to set up an actual server. So this is not done yet. It's not nearly done. But even so, we have some incremental results. And so one test I did was take a small file that contains a large number of objects. In this case, it was 119 objects. And normally this was quite slow uh, to process in HSDS. So without HFIDB, I summarize the number of HTTP requests. There's 334 post requests, 118 put requests, 1,032 GET requests, and took a total time of 48 seconds. So imagine 48 seconds to transcribe what's basically a very small file. And then with the new code, we have 22 post requests and 2 put requests, 1 GET request, and the total time was 12.2 seconds. So a 4x speed up, and I think we're not even finished in optimizing what can be done here. Okay. So next steps. Um, so we want to improve the read performance. So I focus so far on, I've talked about improving the write performance. I would like to optimize the read performance in a similar way. So if it's possible to be able to download all the metadata for a domain in one request. So this would enable you to read any attribute, get any link, uh, just consulting this in-memory database. Um, for dataset reads, it would be interesting to look into some kind of read-ahead logic. So say you have a dataset that's one-dimensional, there's 1,000 rows of a compound type. And if my client code was doing, okay, read a row, look at that, read another row, look at that, then normally that would translate to the number of HTTP requests equal to the number of rows you're reading. If instead the h5pyd was intelligent, it would say, okay, the client's read from row 50 to row 60, and he's probably going to be reading sequentially from there on. So when he asks for row 61, just read rows, say 61 to 70. And then you'll amortize that request latency again, but now on the read side. So and there's some other things that we'll be looking into. But overall, the initial versions with this new architecture will be out in 2 or 3 months, I hope. There's code now in GitHub. If you are brave, you'd like to try it out, you're welcome to. So you can see the branches h5JSON in h5pyd and HSDS. The setup and install are the same as before, so that shouldn't be anything different. And if you have questions or run into issues, feel free to open an issue in GitHub or post to the forum, whatever. All right, that's all I had for this. Any questions? And
Uh,
if no questions on this content, are there any
John,
questions
just
on HSDS or HDF5 in general?
John,
Yeah.
just one question on the you're improving the read performance with
Hmm.
the intelligent read ahead logic.
Right.
Um, are you what are your concerns on that becoming a really thorny thing to try to get all the predictive code in there to really have it work pretty robustly? Because it sounds like that is potentially fairly difficult to do
Right.
in a
Right.
general sense. I mean, it
Yeah.
could. I mean, nothing could be done, but it's pretty resource intensive to get it
Hmm.
right.
Right. Right. I mean, the downside is you guess wrong and you end up reading data that you don't need.
Yes.
Right. And so I think two things is in this first release, just go for low-hanging fruit, basically. Like my example of the one-dimensional data set where the client's just reading row by row. That's pretty straightforward. I think once we get that as a baseline, then we can be looking into other things. It gets more complicated when you have two-dimensional data, right? Because now you are multi-dimensional data. You don't know necessarily which dimension the client may be angling for next, right? So that can be pretty tricky. So I would defer that to later on. The other thing is to do some benchmarking to see where you start to actually impacting performance. So, for example, given the latency of making HTTP requests, going to the server, having the server receive that, retrieve the data, and return it, I would imagine reading one element will have the same performance as reading 10 elements or 100 elements or even 1,000 elements, right? You get beyond that, you may start to see cases where you're taking more time than you would need necessarily. So that has to be monitored. And the other thing is to be uh, considerate of memory usage. So if we end up, I know nowadays, people have a fair amount of memory, but we don't be profligate and start storing a lot of data in memory on a client that is not being utilized, right? So we have to be kind of cognizant of that and have some intelligent strategies. Like if the cache data set data is not being used for some time, makes sense to discard that and free up space for new data. So yeah, but it's a lot of interesting problems. And one other thing I guess I should mention um, is that you have this challenge now where you have, say you have two clients, right? And one is writing to HSDS and one is reading from HSDS. If the before it was not really a challenge to have the current state, right? If your client read something, you got that something. If we're doing this metadata caching and dataset read ahead logic, you won't always have that coherence, right? So
Right.
that's kind of a necessary uh, downside to this. I think in most cases, it should be fine. In cases where it's not, there are methods that can be used to force synchronization, right? And these methods are actually already part of the h5py API, and they come up, for example, with Swimmer. So I mentioned already the flush, right? When you want your current state to be reflected on server, you invoke flush, and that would move any dirty changes out to the server. On the read side, there is a refresh call, and that would say whatever cache data you think you have, discard that and bring in fresh data from the server. So those can be used in cases where you're going to have kind of quote live data and you need to be careful to synchronize that. So it's a little bit of a extra burden on the client. But on the other hand, as I said, you'll get this better performance in the general case.
Yes. And then I guess one ancillary question. When you're designing all the read ahead logic, in principle, um, even a straightforward HDF5 API using the C interface, they have the same read ahead problems if they aren't reading the entire data set in one fell swoop. So
Mm-hmm.
so that problem is really you see it more because of the network latency,
Hmm.
but the
Hmm.
problem exists in the abstract sense, even if you're using the straight C API and want to do the exact same types of things.
Right.
The
Hmm.
implementation clearly would be different, but the logic in terms of the read ahead
Hmm.
might be reusable there for
Right.
somebody who is interested because they face the same problem. It's just not
Hmm.
quite as apparent. But with
Right.
regard to what you talked about in core memory usages, we don't want to do that on the even if we're going through the C API directly to a regular
Right. Right.
HDF5 data store. So that
Yeah.
so that logic, whatever you design there, is useful for other implementations, I would think.
Mhm. Right, right. Yeah, and I think it might be some time before we get to implementing this kind of functionality in the RESTful, which would be
Yes.
the C analog to this. But I think even for H5py, this can be relevant. So like in H5py, you're taught, don't read dataset elements one by one because that's inefficient. Instead, you should, if you want to process like every element of a data set, you should read like a block where a block is big enough to be efficient, but a reasonable memory size, process that block and go on to the next block and so on. And that's fine. It just makes the code that much more complicated for the client.
Yes.
Right? So I mentioned we were going to have h5py readers and writers. And so h5py in this case is like the lower level, talking to h5 library and reading from a file. But on the higher level, we have all the same read-head logic and memory database as before. So with the h5pyd and the h5py reader and writer, that has potential to make things not not more performant than a well-written h5py script, but maybe easier from the coding logic on the client side, because you don't need to worry about being efficient to reduce the number of HDF5 calls you're making.
Yes.
And so
Yeah.
it'll be
Okay.
interesting to see what kind of concrete performance advantages we can get out of that.
Okay. Excellent. Thanks, Sean.
Right. Okay. If there's no more questions, thanks everyone for their attention, and we will catch you next time.
Thanks, everyone. Bye.
Bye bye.